Welcome to the post-class video review of Gibbs free energy. And so let's talk a little bit about laws of thermodynamics, right? So what's the first law of thermodynamics?
The first law of thermodynamics is that energy is always conserved.
Yeah, always conserved. Can be moved around from one place to another. Almost as important is the second law of thermodynamics. And the second law of thermodynamics says that the entropy for the universe is always increasing. So delta S for the universe is always a positive number. And the entropy change for the universe is really, you can think of it as two parts. The system change, and then the surroundings change. Right? Well, in the first activity of this chapter, we learned about predicting delta S for the system. And it turned out it was pretty easy to predict how entropy of the system is going to be changing based on things like temperature and state of matter, gas to liquid, number of molecules.
Things like are either getting more organized or less organized.
Exactly, exactly. And we were pretty good at that. But it turns out the delta S of the surroundings, not so easy, right? Because a lot of times you don't even know what the surroundings are, or they're ill-defined, right? And so in order to use this second law, we had to figure out a way that we could look at the system and talk about the delta S of the surroundings. And so that's what the activity was really about, was making that tie. You know, and I don't think we should really get hung up in all the math kind of that we did to make that tie. Bottom line is that Gibbs came up with this way of thinking about it, and it had to do with the surrounding entropy change was linked to the heat that was transferred. Heat goes out, causes the molecules to move around, more entropy, and vice versa. If heat comes in, that means that the surroundings lose that energy, lose that entropy, right? And so he, for whatever reason, he didn't want to cast it in terms of entropy, and so he came up with his own term, free energy. And because he came up with it, they named the symbol after him.
There you go.
Right, so bottom line from the class was that one important equation, delta G equals delta H minus T delta S. Couple things about this equation. One is that this is always valid.
Always.
Except when it's not. Right? And it's going to be important later on to know when you can't apply it. The second thing is that these all have to be talking about the same thing. Delta G for the system, delta H for the system, delta S for the system. Delta G for the reaction, delta H for the reaction, delta S for the reaction. So it's always cast in terms of what you're actually studying. Okay, so bottom line is that's the most important equation from the day. That's what you need to remember. That's what you need to be able to learn how to use. So we're going to go over an example of using this equation.
Okay.
So here's our test example. Nitrogen gas plus hydrogen gas creates ammonia. And it's kind of an important reaction. This is where we get the ammonia that goes into things like fertilizers and plastics. And I've seen a report that said that this process is responsible for using about 5% of the electrical energy, industrial energy in the United States.
That's a lot.
That's a lot. So let's look at that. Can we predict what the sign of delta S is for this reaction?
Right. Well, you're actually going from more molecules to less molecules. Yeah. So you've actually decreased the disorder. Right.
Exactly. More molecules to less order, delta S is negative. Right? So that's a negative factor here. But if we want to use that equation, we actually need numbers.
Okay.
Where do those numbers come from?
Experiments.
Experiments. Somebody's measured a lot of these numbers, and so we can look them up in tables. And there are tables in the back of your textbook that have these numbers written down. And so these are the two numbers that I looked up. Delta H, negative 92.3 kilojoules per mole. Delta S, negative 360.64 joule per mole K. And so we were right. We predicted a negative delta S, and that's what it actually is. And so we can use these two numbers to predict qualitatively, is a reaction going to be spontaneous at low temperatures or high temperatures?
Well, let's think about our equation of delta G.
And remember, the conditions for spontaneity for delta G is that it has to be less than 0. It's the opposite of entropy.
Right.
Okay, so we look at the enthalpy. Well, that's a negative number, so that's great. That's going to make it spontaneous.
Right.
How about the entropy?
Well, that's going to depend because it's a negative number. You're multiplying it by another negative, so it's going to come out to positive. Whether or not that's bigger than your enthalpy is going to depend on temperature.
Yeah, how big the temperature. If that's a huge number, you're multiplying a huge number, you get a big positive number there, it overcomes the delta H.
Right.
So we predict that this is going to be spontaneous at low temperatures, not spontaneous at high temperatures.
Right.
Well, we can figure out the temperature that it crosses over by assuming that, well, when you go from negative delta G to positive, it goes through 0, right?
Right.
And so when delta G is 0, that's the crossover point. So we just set 0 equal to that, and then after a little bit of algebra, you take this over to that side and do the cross multiplication, you get delta H over delta S equals the temperature where delta G is 0. And if we plug these numbers in, the one thing we have to make sure is that we have the same units, right? Delta H and delta S have to have the same units. And so this is in kilojoules, this is in joules. Easiest thing to do is move this decimal 3 places over to get kilojoules. So negative 92.38 kilojoules per mole divided by negative 0.36064 kilojoules per mole gives us the temperature. Do that calculation, 256 Kelvin, or negative 17 degrees Celsius.
Right.
Okay? Now the curious thing about this is that, like I said, this is an important industrial reaction. And in industry, this reaction is run at 500 degrees.
How do they do that?
I thought we said that it's non-spontaneous at higher temperatures.
Me too. I was there when you said that.
Yeah. So we predict that this is going to be spontaneous at low temperatures, not spontaneous at high temperatures.
Right.
Why would they do that? Why would we run this at high temperature if it's non-spontaneous?
No idea.
No idea. So there are ways to get around this idea because this is actually applicable only at standard conditions, and that's something we're going to learn about in the next class. And so you can alter the conditions to make something that's not favorable, favorable, or something that's not spontaneous, spontaneous. And the reason they actually run this at high temperature is because this reaction is really slow. And in the chapter 14 on kinetics, we learned that if something's slow, you want to speed it up. What do? Raise the temperature. So these things are all kind of tied together. And that's something we have to keep in mind. Hope this helps you understand Gibbs free energy, and we'll see you in class.